afternoon, everyone. I am Jeong from Baylor University. My advisor is Professor Lee. It is a great honor for me to present our research work in the Sensors Conference. I present on behalf of the first author in this work for the travel issues. So, interstitial cystitis or IC is a chronic condition, and 2.7 to 6.5% of the American population are diagnosed with IC. This condition causes bladder pain and pressure and more. This disease also linked with other chronic illness, such as end-stage renal disease. Other conditions connected with IC are irritable bowel syndromes, chronic fatigue, and etc. A study revealed that around 11% of women with IC experienced suicidal ideation. In addition, IC is a significant predictor of anxiety, depression, and insomnia, resulting in hampered social life and impaired quality of life. So there are certain challenges with IC diagnosis. For effective treatment processes, it requires early diagnosis and personalized treatment strategies. Some other diseases such as urinary tract infection, chronic pelvic pain syndrome, overactive bladder have similar symptoms like IC. So it becomes difficult to differentiate IC from other conditions with similar symptoms. Therefore, developing a highly sensitive device with accurate, rapid, and multiplex detection capability of different IC biomarkers on the same chip for personalized, continuous, and real-time monitoring at the point of care is crucial. Urine biomarkers like interleukin-1 alpha or IL-1 alpha and vascular endothelial growth factor or VEGF levels are significantly elevated in IC patients compared with healthy individuals or overactive bladder patients, suggesting that urinary metabolites like interleukin-1 alpha and VEGF can play a crucial role in IC diagnosis. So why electrochemical sensors? Some of the conventional methods such as ELISpot assessment is unable to provide a quantitative measurement of cytokines. Also, PCR requires days to process sample in the lab facility and getting the lab test result. On the other hand, electrochemical sensors facilitate on-spot rapid detection and continuous quantitative monitoring at point of care. The sample handling and analysis process is simple, and the fabrication process is inexpensive. The sensing performance of this sensor show good sensitivity and suitability for real-time monitoring. So in this work, we report a high-performance and nano-engineered electrochemical sensor for continuous monitoring and detection of multiple biomarkers, such as the interleukin-1 alpha and VEGF in real time for IC diagnosis using a single chip at point of care. So the sensor design consists of two working electrodes, one reference electrode and one counter electrode. So the fabrication process began with designing the electrode pattern, which was cut on the vinyl sheet using craft cutter. Next, the sensor design was transferred to a glass substrate by attaching the adhesive vinyl pattern as masking and covering the reference electrode segment with tape. After that, the material deposition of working electrode and counter electrode was completed with gold deposition using electron beam evaporator. Next, the tape on reference electrode was peeled off and the other three electrodes were masked with tape. The reference electrode was screen printed with silver chloride paste and cured. Finally, the vinyl sheet and tape were removed, leaving behind the compact sensor. So here is the functionalization process for interleukin-1 alpha and VEGF electrode that I would discuss briefly. For interleukin-1 alpha functionalization, working electrode was treated with hydrogen peroxide and ammonium hydroxide to generate hydroxyl groups. Then the sensor was immersed in the PHP and dimethyl sulfoxide, DMSO solution to form a PHP layer. Next, the carboxyl groups were activated using EDC and NHS. The non-specific sites on sensor surface were blocked with BSA solution. Then the working electrode was immobilized with interleukin-1 alpha antibodies, and finally the functionalized interleukin-1 alpha electrode was tested with interleukin-1 alpha urine sample. The VEGF electrode was functionalized with molecularly imprinted polymer, MIP, coupling method using OPD, and VEGF solution in acetate buffer and tested with VEGF electrode, VEGF urine sample. So here are the electrochemical measurements for interleukin-1 alpha electrode. The CV responses of different functionalization coating showed a decreased current compared to the previous coating through hydroxylation process with PHP, carboxyl group activation with EDC and NHS, BSA functionalization, anti-interleukin-1 alpha by electrode immobilization due to non-conductive nature, negative charge repulsion, and immunocomplex formation. Both CV and CA methods show lower current level when exposed to anti-interleukin-1 alpha with a sensor response time of 15 seconds. In figure C, CV responses show decreasing peak current with increasing 8 different interleukin-1 alpha concentrations. A linear relationship between peak current and interleukin-1 alpha concentration was found from where the limit of detection LOD was calculated to be 1 femtogram per milliliter using 3 sigma per m criteria, where sigma represents the standard deviation and m is the slope of the calibration curve. The sensor characterization for VEGF detection is depicted here. The MIP electrode for VEGF detection was compared with Baylor electrode via CV scans in electrolyte solution, where the redox peak decreased in MIP electrode due to non-conductive OPD film. The CE measurement were consistent with CV result, showing lower current level in MIP electrode and sensor response time of 20 seconds. After that, the electrochemical measurement was performed for VEGF concentration from 1 to 1,000 picogram per milliliter. Figure C shows that the higher VEGF concentration resulting in lower oxidation peak current due to the kinetic barrier caused by VEGF binding to the MIP receptor, creating the uninsulating effect. In the calibration curve at figure D, linear relationship was found between oxidation peak current and VEGF concentration, and the limit of detection LOD was calculated to be 10 femtogram per milliliter. The reproducibility and selectivity analysis were performed for both interleukin-1 alpha and VEGF electrode. In the reproducibility assessment, CV measurements were performed using 50 picogram per milliliter interleukin-1 alpha and 200 gram picogram per milliliter VEGF sample, and the tested were repeated for 3 identical multiplexed biosensors. The result in figure 1 showed excellent reproducibility for both interleukin-1 alpha and VEGF working electrode with a relative standard deviation of less than 3%. The selectivity testing was conducted with 3 artificial urine solutions. First one, just interferent. We used the 0.5 millimoles glucose and 80 nanomoles nitrite. Second one is the 50 picogram per milliliter interleukin-1 alpha mixed with interferent. Third one is the 200 gram picogram per milliliter VEGF mixed with interferent. Interferent solution results show no current change for either interleukin-1 alpha or VEGF working electrode or only interferent sample. Interleukin-1 alpha mixed with interferent sample introduced significant increase in current for interleukin-1 alpha working electrode, but no change for VEGF working electrode. For testing using VEGF mixed with interferent sample, VEGF working electrode show a current spike, while interleukin-1 alpha working electrode had no response, demonstrating high sensor selectivity for both sensing electrodes. So in conclusion, successful fabrication of multiplex biosensor for detecting interleukin-1 alpha and VEGF biomarkers in urine was achieved. The clinical application of this sensor aims to improve diagnostics, detection, and continuous monitoring for IC patients. In the case of performance, the electrochemical sensor array demonstrates excellent sensitivity, low detection limit, reproducibility, and selectivity. The future work is focused on detecting additional urine biomarker related to the IC and implementing the relation between this biomarker for more accurate diagnosis of IC, despite of having overlapping symptoms like a similar health condition. Design improvement as a whole device plan for a flexible, compact, and user-friendly data acquisition unit based on an integrated circuit for point-of-care diagnostics. Thank you for listening to my presentation.